Alright, welcome back. Thanks for tuning in again. So this weekend I want to take a look at this beast here. This is a 1965 Onan powered by an 884 cubic inch V8 Roline or Royline, however you want to pronounce the name, natural gas engine. Now, there's a couple issues with this unit. We're going to go into that in a second. I just want to really assess the thing and see what the extent of the damage is, or if there is any damage. I don't exactly know what's wrong with it. So let's take a walk around the unit. Yes, this is an 884 cubic inch V8 spark ignition engine powering this 140 kilowatt Onan genset. Here's a look at the Onan tag. It's a 140 WE, built in 1965. Now there's some conflicting, well, as far as I can tell, conflicting ways to say that name. Royline, Roline. I kind of call it Roline, but somebody will correct me, I'm sure. It's a pretty large unit. Let's take a look at the engine tag. It's an H884U. 5 3/8 by 4 7/8. So, a little bit of back history, just a little bit. You see it says Waukesha Motor Company there. So the story goes, at least from the little bit of research I've done, is Westinghouse Air Brake Company bought out Leroy. Most people have heard of Leroy. They've been building engines and power units, well, they had been, since before World War I. Now, Westinghouse bought out Leroy in '54, but in '58, Westinghouse Air Brake sold the engine division, Leroy engine division, to Waukesha. It's interesting for me. I see a lot of medium-sized Waukesha engines powering generators out in the field. Primarily, I see the F817 Waukesha and the F1197. It's interesting that this 884 cubic inch engine kind of sits right in between those two, the 817 cubic inch and the 1197 cubic inch. But those are both big inline sixes, you know, the standard big industrial inline six that Waukesha had been building for decades. Now, a couple specs. I'm reading this from a little cheat sheet here. I don't have all this memorized. But the Waukesha F817 had a bore and a stroke 5 3/8 by 6 inch, so it was an under square engine. It weighed 2,750 pounds and put out 190 horsepower at 2,000 RPM. The next step up, or at least what I see in the field on generators, was the 1197, which had a 6 1/4 by 6 1/2 bore and stroke, weighed 4,050 pounds, and made 248 horsepower at 1,800 RPM. Well, this thing here had a 5 3/8 bore and a 4 7/8 stroke, so it was an over square engine. It only weighs 1,900 pounds. This, and when I say that, I mean the bare engine. So from here to here, the engine itself weighs 1,900 pounds, and it was made 360 horsepower at 3,000 RPM. So really, this, I don't want to say this engine was advanced for its time, but it was really a step in a different direction from the traditional big heavy inline sixes. But it didn't last very long. They stopped making the Roline line in about 1974. I don't know when exactly this engine went out of production, but by '74 they were pretty much done. Whereas, you know, I've seen Waukesha F817s on units from the 90s, so definitely they had a longer run than this. Really, there's not many of these left out in the field. This is the only one that I knew of, and it's not in the field anymore. So there's a little bit of history on the engine. Now for a little bit of history on this genset itself. It's got 1,662 hours on it. It was owned by the same site, or the same customer, that had that small 30 kW unit with that inline 6.4 that I took a video on a few months ago. Pretty much the thing is, the story goes is, well, it's not a story because I was there. So the thing ran for about 28 or 30 hours and then shut down. These old units, they don't tell you what fault occurred. This little emergency relay just pops up and the red light comes on. This is a cranking limiter. So it could be low oil pressure, high engine temperature, or overspeed. Those are the three faults that this thing has. So I got the service call about 10 o'clock on a Saturday night, went up to the customer. Building was completely dark, they still had no power, and they probably weren't going to get, well, they weren't going to get power until later the next day. So I get on site, go in, take a look at the thing. First thing you do, you check oil level and coolant level. Everything looked okay there. Went around, made sure there was no belts had hopped off the unit, and nothing was loose. And went over, checked the battery. Battery still had some life left in it. And reset the fault, cranked it up. It started right up and it seemed to run okay. I observed the unit run for about 20 seconds. And during that 20 seconds, I noticed that the engine speed was slowly increasing. And it kept increasing until the unit shut down on overspeed. I had to actually manually reset the overspeed switch because it's stuck closed. So I'm like, alright, well, must have governor problems then. So we got a mechanical governor right here, flyweight governor, and a vacuum booster. And move on to the other side. So mind you, it's still, the power's out, there's no lights in this building. Luckily I had a flashlight and a headlamp with me. So the governor itself seemed to move free. The linkage wasn't binding. The line for the vacuum booster didn't seem to be cracked or anything. So right off the bat, I reset the fault and restart the unit and observe the governor closely. The unit would come up to about its rated speed, about 1800, but then it would continue to slowly increase in speed until it would shut down, and it did that repeatedly. So over the next half an hour or so, I tried all of the tricks in the book to try to get this governor to hold at 1800 RPM. Whether it be adjusting the linkage here, the link between the governor arm and the throttle, taking the vacuum booster out of the system in case there was a vacuum leak around the diaphragm, which happens on these, when these things get 50 years old. That diaphragm will start leaking, you'll get a vacuum leak. Looking at the governor, let me go around back to the other side. Adjusting the, this is, oh, sorry about that. This is the actual, your speed adjustment right here. That nut on that threaded rod attached to the spring, and that spring is attached to a lever arm which actuates the vacuum booster plunger, or the diaphragm. We'll go into that more in a second. Tried everything I could to get the thing running right, and it just would not maintain a speed. It would continue to overspeed. And I had seen something similar to this before on a different engine. It was actually on a Hercules engine, on a small Kohler genset, where the thrust bearing in this governor, or in the governor, completely different configuration but same concept, would actually wore out, and that resulted in the flyweights not being able to physically push the governor arm far enough to idle to allow it to operate, so, or to allow it to control its speed. So I have a feeling that's what we're going to find in here. Now, on a second note, as I was test running this unit, trying to get it to run correctly, I realized that there were some serious exhaust leaks in the exhaust system for this unit. So it's got this Y pipe here and these two flex sections, one on each exhaust manifold, coming up, and it went to a common point with another piece of flex to a large muffler. That large muffler had a few leaks in it, a few holes, actually rust holes, and the room I was in was quickly filling with carbon monoxide and exhaust gas while I was testing it. So even even if I did get the thing running, I could not have, you know, actually put it back in service, because those exhaust leaks could have killed someone. They were pretty bad. So at that point I had to tag the unit out of service. It could not remain in service. We brought a temp generator in just to get them back up and running, get the building powered back up. So that's my little story on this unit. We ended up quoting the customer to replace the exhaust system and to do further troubleshooting on the governor here. The customer opted not to repair the unit or the exhaust. They opted to install a new genset and ATS. So that's why this thing is in my hands right now. But I'm curious to see what ails it. Okay, before we tear into this thing, I want to talk real quick about how the governing is set up in this engine. We got a few main components, 3 really. The mechanical governor, the vacuum compensator or the vacuum booster, and the intake or the throttle butterfly of the engine. So when the engine's not running, it's not rotating, we've got no manifold vacuum, no nothing. We've got this spring here under tension and this spring here under compression. The flyweights in the mechanical governor are going to, if you can picture my hands here being the flyweights, where they pivot on like the palm of my hand here, they pivot like this. They're closed, they're down like this, because this spring is under tension. So this lever here rotates like this on this central pivot, and this lever arm here is attached to that, so it's forcing, this is being pulled this way, so this is forcing the spool down to close the governor weights. So when the engine is initially started, well, let me go back a step. When the engine's stopped, not running, not turning, the throttle is at the wide open position. When the engine is started, the shaft here for the governor begins rotating. As the engine increases in speed, the weight of the flyweights causes them to actually fly out. The centrifugal force rotates them out. My thumbs are the lever arms on the weights. The lever arms push up on the spool of the governor, which rotates this lever up, which increases tension on this spring. It overcomes the tension of the spring, I should say, till it reaches the point of equilibrium, and it pulls on this rod here, which closes the throttle butterfly. Now, at that same time, once the engine reaches its no-load rated speed, the throttle butterfly is almost closed, almost completely closed at no load. Manifold vacuum, as a result, is very high, and there's a little copper line that runs from the intake manifold to the housing of the vacuum compensator or vacuum booster. This chamber is now at manifold vacuum pressure, and this kind of little, round area down here represents the rubber diaphragm of that vacuum compensator. The vacuum causes the diaphragm to be pulled up or pushed up by atmospheric pressure, compressing this spring, and that, because of this little bell crank lever here, moves this lever up, which slightly releases tension on this governor spring. It's a little bit complicated, it's a little bit convoluted, but it's basically, the vacuum booster is a means to increase the sensitivity and decrease the reaction time of the mechanical governor. So now picture this. The engine's running at rated speed, no load. The governor flyweights and the governor spring are at their point of equilibrium. The manifold vacuum is not changing, so the diaphragm is not moving. The vacuum booster diaphragm is not moving. So that's at a set point, which is allowing this spring and these weights to find equilibrium to hold the engine at 1800 RPM. Now, say a load gets dropped on the engine. First thing that's going to happen is the crankshaft speed of the engine is going to drop. The throttle butterfly is not going to immediately open. Now, again, we're talking, tenths of a second this is going to occur. As the engine's rotation, the engine speed drops, manifold vacuum is going to go down because, manifold vacuum is going to go down because there's less volume of air flowing through the engine. When manifold vacuum drops, that allows this spring to extend the diaphragm out, push the diaphragm down, because remember, there's less atmospheric there's less pressure differential between the atmosphere pushing it up and the spring pushing it down. When that occurs, the bell crank, this lever moves back, increases spring tension just slightly, and allows the weights to be forced closed with just a little bit more effort to crack the throttle enough to bring the engine back up, and then equilibrium is then found again. Granted, manifold vacuum is lower because we have the same engine RPM but a wider throttle opening. That being said, even though that's the case, we still will find equilibrium between this spring and these weights to maintain 1800 RPM. It's a little bit difficult to think about for me because there's a lot of variables here, but it really helps to know this kind of operation, or at least see the cross-sectional view of this operation, especially when you're out on site trying to troubleshoot it and you don't really know what you're looking at. So I hope that this is a little bit helpful to anybody that may be out in the field and seeing some of this older technology still in service. So enough yapping, let's get to the teardown. Okay, how's that for a vantage point? Hopefully you can see what I'm doing here. So first, let's just start tearing the governing system down. I don't even want to try to turn the engine over before we get into this because I know it's going to overspeed. So let's go ahead and pull off the throttle link rod here. Now, one thing I will say is there's quite a lot of spring tension this governor has to overcome to move that throttle to mostly closed, which is where it's going to rest. It's not going to rest at fully closed with the engine running at light load. It's going to be a little open, but not much. But that's a lot of force to overcome. So let's go ahead and pull this off. I think I have all the tools I need right in this area here. So I don't think I ever said what I think the issue is here. Maybe I did, I forget. I think I did, something about the thrust bearing. So, and I should have pointed it out when we were over at the table looking at the diagram. But there's going to be a thrust bearing somewhere in here to allow that force to be modified so not so much friction is caused when those flyweights are trying to overcome that spring tension. But we'll get into that once we take the governor apart. So that's disconnected. What's this? The 7/16 here. Yep. This is the vacuum line from the intake manifold, from one of the intake runners to the actual booster body itself. I'm just going to move that out of the way. I think I'm going to take the whole vacuum booster and bracket off. There's just 2 bolts there. Got a little swivel socket here, make it a little bit easier. That bolt in there for now. Let's see if I can unhook that spring. Come on. There we go. So there's the vacuum booster assembly and its bracket. Does that look a little bit like a little diagram I just drew? The booster, that little bell crank there. It should. So let's set that aside. And that leaves the governor itself. See that spring there? That's a pretty heavy spring. Take that and just threaded rod out, if I can. There we go. Set that aside, and the governor looks like it's only held in with this 2 bolts here, or 2 nuts. Looks like it's sitting on studs. They weren't all that tight. I've never had this apart. Let me just say that too. A lot of people think I might be staging these videos. That's not the case. What's that nut at? You're seeing it in real time as I'm seeing it. Washer right there. Okay. Actually, let me take this. That should just lift right out of there. It's actually... There you go. Oh, it's a pierce, okay. It's either going to be a pierce or a hoof. Make of the governor. Alright. Well, let me set this aside. Oh. Thought I heard something in there. I hear the fly weights. I also hear some crunchies in there. Shouldn't be hearing that. Okay. Well, let me get down for a closer look here. Alright, so the governor seats right here in the valley. Got a little gear on a shaft there, a little lay shaft, probably the same one the distributor's driven off of. I imagine there's a run of timing gears going up the front. Probably drives the distributor on one side and the governor here on the other. Alright. Got a little oil line there, and looks like we got an oil hole. Let's look at the teeth of that gear. Wow, they look awful narrow. Huh? Look at the tops. Awful narrow in the center and awful wide on the outside. Well, let's get these parts onto a bench. Nice, okay. Okay. Alright, well, let's take a look at the governor, mechanical governor itself first. We'll set the vacuum booster aside. So, looking at it, boy, the first thing I noticed is that drive gear. Just like the gear in the block, you can see just how worn these teeth are. Compare the end of the tooth, the width across the flat, across the top. Can you see that? Toward the center, and then back at the end. The center is worn. It's actually very, very sharp, like razor thin. Wow. Boy, this wouldn't have ran much longer. And that's startling, because all that material is in the engine. All that material is in the oil pan now. So, let's go ahead and pull the guts out of this thing. It should be pretty easy. Looks like we got 4 screws, 1, 2, 3, 4. And I imagine the whole top housing will lift right off. I hear there's some stuff shaking around in there. So, let's see. Did I grab the right screwdriver? No, I didn't. Oh, there it is. Okay. Somebody mentioned in one of my other videos that I should get an electric screwdriver or something like that. I don't want an electric screwdriver. I like doing it manually. What the hell do I want to listen to what I'm taking out a screw for? Three, four. Oh. Oh, that's interesting. Some bits came out. 3 bits. Okay. Well, there's the governor assembly. Looks like we got 4 weights. Now, can you kind of see what I was trying to get at in my little picture there? Each weight has a little foot on it. You probably can't see because of the lighting. Let me move you around over here. Alright, is that lighting a bit better? Maybe. See the little foot on the governor weight? And then this here in the center is the spool. It's got a flange at the bottom and a flange at the top. It's recessed to allow the weights to close. So, alright. Wow, everything feels sharp in here for some reason. There's your thrust bearing. Something don't look right about that. Yeah. Something didn't right about that at all. Yeah, can you see the spool better now? Wow. Yeah, this thing is toast. Look at the balls. They got flats on them. You know what? That was something that fell out. I think one of these little balls. It's one of the balls fell right out of the thing. And look, you see the scars up at the top and the top of the shaft here. That was the problem, I think. You can see the wear on the bottom, the foot there as well. The whole thing's worn out. Friction. I don't know what these are from. These fell out. Let's look at the housing here. Oh wow. Look at that groove. Look at that groove that's worn. The entire diameter of the housing. And that's definitely from the weights rubbing. That doesn't appear to have been in there on purpose. And see the 2 points on this fork here, that's where the thrust bearing is supposed to contact. They're pretty well beat too. Look how dirty it is in there. All of this is probably because of where this governor sits on the engine. Right at the very top. Yeah, look at the grooves on the weights there from rubbing on that aluminum housing. Alright, well I apologize if that previous scene or that previous clip was washed out. I realize I need to put more consideration into the lighting in my videos. So I've moved inside and hopefully you can see a little better now. So I've disassembled the mechanical governor completely. The drive gear here is a press fit onto the shaft, just like on a distributor or an oil pump, something like that. So we got the housing, the lower drive housing with a bronze sleeve bearing there. Got a nice thrust bearing here at the bottom, at the lower end of the shaft. This would be like the governor shaft or the governor yoke, you might call it. I've removed the flyweights. They were just held on with these pins here, and you can definitely see the punishment that they took. If that will focus, you can see where the material has just been, come on, focus on that. There you go. The material has just been rolled over on that foot there of the weight. Just completely brutal. All of them have this same wear. And you can't see it on the back of that one, but you can see the scuffing. There it is. See the scuffing on the weights themselves from flying out too far because of all this wear. They were hitting the housing. Let me take the spool, the governor spool, off the yoke here, and you can see that same wear reflected on the bottom of the spool. Will you focus on that for me? There it goes. Pretty rough. So this foot acts on the bottom of this spool. Okay. Now the upper thrust bearing, the lower race won't even come off of here. The top race, you can just see the heat and the wear, just the grinding that was occurring while this thing was running. And then this was floating around in between the upper and lower thrust bearing race up here. This little is a retaining clip that rides in this groove, and then whatever the hell that was. These pieces that fell out initially, I think they may have been part of the cage for this upper thrust bearing. These three chunks, I don't know what they came from. Like I said, I think they made up a cage for these balls here, which can't even really call them balls anymore because they're not round. That one's got a crater in it. Look at that. Several of them look like that. Can't even really call them ball bearings anymore. So this governor is toast. There's really even no rebuilding this, in my opinion. Even though you could save this governor yoke if you had a mind to. I mean, the upper, there's a bronze sleeve bearing in the housing that rides here. That's torn up. Really, this whole assembly is junk. So I believe the root cause of this failure is shared between Pierce, the company that made the governor, and Onan, who utilized, or maybe not Onan themselves, but maybe Waukesha, Rolene, in the configuration of this governor on their engine. So what I believe occurred is a lack of lubrication. So we've got an oil hole here, and this yoke is drilled to these two outlet holes, one here and one there. It's just cross-drilled through there. Now, oil is admitted to this hole through the hole on the lower bearing here. The problem is that's not, see that hole right there? Oil enters that hole, sorry about that, and it exits that hole in the bearing, but there's not a groove cut concentrically in the bearing. So the actual movement of the governor, the flyweights, the thrust bearings, only see lubrication for 20 degrees of rotation of the shaft. And you know, this shaft is flinging around pretty quick. That's, you know, 20 degrees out of 360 degrees of rotation is not very much flow of oil up to where all the force is to on the within the governor itself. So, like I said, I think I blame Pierce for that, but I blame the application of the governor in regards to how much force the governor has to overcome in the way of spring tension to actually operate. So, you know, the point is moot, but I don't think there's any saving this governor. So right now, the unit may run, but it won't run as a generator because it doesn't have a governor. So if you guys have any interest, I'm thinking about doing an electronic governor conversion on this unit. Let me go back out to the unit, we'll talk about that. So it's interesting because this is the situation that the customer would have been in had I done more troubleshooting and found this failed governor on site. And really, if this unit was to remain in service, I wouldn't repair that mechanical governor. This thing would get converted to an electronic governor, which would entail blanking that plate off, or making a blanking plate for this, installing a speed sensor, a mag pickup we call it, in the bell housing to count the flywheel teeth as they go by, installing in an electric actuator to operate the throttle, and a governor controller, the brains of the operation, somewhere in the control box. So I think I have enough parts around that I can scrounge up to actually convert this thing to electronic, if you guys had any interest in seeing that. I definitely want to try to get this thing running if the natural gas supply to my house will feed it. So that's about all for this video. Sorry we didn't get it running, but yeah, it is what it is. Alright, catch you on the next one.